Good morning. Today we are gonna learn about the important topic named semaphore variable. Semaphore variable are blocking construct. It is OS based synchronization mechanism. It is used for multiprocess solution. It is a general purpose utility. It is designed by legendary Dijkstra, and it implemented as abstract data type. Semaphore operations are atomic, or semaphore operations include wait uh, and signal. Wait is also known as down and P. Signal is also known as up and V. Semaphore operation are activated from user applications like system call. Okay. There are two types of semaphore variables. One is binary semaphore variable and other is counting semaphore variable. Binary semaphore variable takes value 0 and 1, and also known as mutex, mutually exclusive. And counting semaphore variable takes value from minus infinity to infinity. Counting semaphore, the structure of counting semaphore variable looks like this. It contains an integer value and a Q type. Q type is basically the list of PCBs of those process that gets blocked while performing down operation unsuccessfully. So what is a Q type? Basically, this Q type means uh, it contains the list of PCBs that get blocked while doing the down operation. How does the process can get blocked during the down operation? If the value of the counting semaphore value becomes less than 0, then that process gets blocked, or which means that the PCB of that process is added to the block queue. Um, okay. So how that block process again wake up if another process execute the operation, then in FIFO manner, the first block process is waked up to execute, or to execute the critical section, or to use the resources. Positive value of semaphore variable indicates that those many down operation can be successful. Negative value of counting semaphore variable indicates number of block processes. So if the value of S value go is less than 0 and an up operation is called, then what happen is that it select the process from the queue, the block queue, and wake it. This selection can be based on any manner such as LIFO, FIFO, or priority. Another type of semaphore variable is binary semaphore variable. Binary semaphore variable, as the name suggests, binary means it can only take 0 or 1. The structure looks like it an enum value 0 or 1 and a Q type L. Similarly, in this the Q type L suggests that it contains list of all the PCBs that gets blocked while doing the down operation. If the value of binary semaphore value is 0 and a down operation is called by some process, then that process gets blocked, and PCB of that process is added to the block queue. Binary semaphore value 1 indicate that one down operation can be successful, and binary semaphore value 0 indicates that the queue is empty, either the queue is empty or the queue is not empty. Queue is empty means there is no block process, and queue is not empty means there are some block process in the queue. Classical IPC problem. First one is producer consumer problem. Producer consumer problem makes use of two semaphore variable. One is counting semaphore variable to note the amount of free space, or the amount of space in the buffer available, and binary semaphore variable to access the shared resources. In this case, the shared resources is buffer. So when a producer want to produce a good, it first check does the buffer is empty. If not, then it calls the wait operation on semaphore on a mutex or binary semaphore variable to modify or to produce an item and increment the number of item in buffer by 1. Then that exit section, just like opposite of that of the entry section. First, the mutex, the signal operation on mutex variable is done, and then signal operation on full is done to indicate that uh, there is one less space available uh, than before. Similarly, for consumer, first it check does the it's first check that there are item in buffer. If there is no item in buffer, then it just stop there. And if there is an item in buffer, then the consumer goes on to execute wait on mutex uh, uh, to the shared resource to access the buffer in an isolated manner. Then signal mutex is executed, and then signal empty. Reader writer problem. There are okay, so there are two types of reader writer problem here we are going to discuss. First is there is only one reader and there is only one writer. This one reader one writer problem is very similar to that of producer consumer problem. So like only one of those two can access the shared resources in this. Either the reader is reading the book or writer is writing the book. But in general cases, in normal day-to-day cases, the situations is more of like a second case where there can be many readers and many writers. So, like first reader writer problem. Okay, T1, T2, T3. No, missed a lot. Okay. So first one is very easy. Okay. Yep. So first one is very easy. Like either the reader is allowed or writer is allowed. If reader is reading, then writer cannot enter, and if writer is writing, then reader cannot enter. But in second problem, it's a little bit complex. First of all, like if there is like no one in the room or no one is reading a book, then anyone, either the reader or the writer can enter. If reader enters, then like one book can be read by many readers. Therefore, subsequent reader can enter, but a writer cannot enter. Writer has to wait till the time that all the reader has left the book or just left the library or the book. In this case, we are prioritizing reader and writer will starve. Like if reader just keeps on coming, like first reader one is there, then reader two came. Then when reader two is reading, reader one left and reader three came. But in between, if assume like W1, the writer one arrives, then it just keeps on waiting until all the reader leaves the book or the library. So in this, we are prioritizing reader and writer will starve. Another way to deal with this is like if like first of all case first case remains the same. If no one is reading, then either like no one is using the book, then either reader can read the book or writer can write the book. Assume like here again, if reader is reading the book and W1 came and writer came. After that, so writer is currently waiting to finish. Is waiting for reader 1 to finish reading the book. While waiting, multiple readers came, like reader 2 and reader 3 came. Then that reader 2 and reader 3, sorry, reader 2 and reader 3 has to wait until W1 has written the book. So in this, if any readers first enters first, then all the reader enter, and writer will wait star writer. This is the above case we discussed. Yeah, but in this case, if any writer will enter, then all will wait. Like if any writer is waiting, then all the other writer and reader will wait. This starve the reader and other writers. It will starve the reader and other writer. This is, I think I might have done some mistake here. No, it's just like this. Yeah, I think I just did that. Yeah. Okay, cool. No, it's this is like till all readers goes out. R5 is waiting until free from all readers and waiting writers. This is the second case. That is the continuation of the first one. Sorry. Starvation to readers only and writers are prioritized. It is a principle of turnstile. That was just the continuation of this one. Both the case was explained. The second case is this one, in which we are prioritizing writers. Second is dining philosopher. In dining philosopher, there are five philosopher sitting in a circular table, and like each philosopher has a fork on its left side. So like yeah, on both of its side, like you can say there is a fork. So there is only like if this is a circular table. So this is fork one, this is fork two, fork two, fork three, fork four, fork five. So everyone has a fork to its left, which means like there is only five fork, and either they eat or think. If they are eating, then they if reader is sorry, if like philosopher is tired of thinking, then he eats. So how does this dining philosopher take place? Like here, if first the philosopher is thinking, after thinking, it takes the eighth fork, and then eighth, like you can say like first of all it takes like if this is one, let's choose um this is one, this is two, this is three, this is four, this is five. So this is the ith fork, well, the one fork, fork one, and this is fork two, this is fork three, four, and five. So, like if we take the example of first thinker or philosopher, so if like I equals to one, so if he after he thinks, it takes the fork one F1, which means that would be his right fork, and after taking the right fork, he will pick the left fork. So and then he eat, and then he put again the right fork, a right fork, and then the left fork. So, what happened in this case is like all the five philosopher picks the folk at the same time. So, like one like philosopher one will pick the folk one, philosopher two will pick the folk two. Similarly, three philosopher three will take the folk three, and it goes on. So, what happened when philosopher 1 tries to pick folk 2, but it is not available, so it will wait for philosopher 2 to finish, but 2 is waiting for 3, 3 is waiting for 4, 4 is waiting for 5, and 5 is waiting for 1, which means it is it becomes a deadlock. Therefore it suffers from deadlock. Like when it suffers from deadlock, if everyone wants to eat at the same time, to prevent the deadlock, there are ways. First, one of them is uh, to use non-semaphore. One is like using semaphore, and one is like non using non-semaphore. What happen in non-semaphore, that like there are n philosopher, so n minus one will first take the left fork and then the right fork. But that one philosopher will first take the right fork, then the left fork. Thus, deadlock will not happen. Thus, avoiding deadlock. So in the above case, like when we have five philosophers, so four philosopher like first take four philosopher either take the left fork, then the right fork, or the right fork, then the left fork, and that one philosopher just do the opposite of the rest four. Second is that having an extra fork. If instead of five fork there are six fork, then one of the philosopher will able to complete its eating, and then pass the fork to other philosopher, completing the whole process using semaphore variable. And second is using semaphore variable, which ensures mutual exclusion on taking the fork. This is like the complete program using semaphore variable. You should go through it. Okay. Concurrency means two or more action in progress at same time. Sorry for the noise. Yeah, grinding. Grrr. Okay. Concurrency means two or more action in progress at same time. Parallelism means two or more action executing in parallel. Okay. Type of concurrency, pseudo concurrency and real concurrency. Real concurrency means parallelism. Pseudo concurrency matlab like on a single uniprocessor system. Well, Let S1 and S2 be two statement and does not have shared resource or variable, then output of one does not serve as input to others. Okay. If Bernstein's condition. Okay. Okay, this is para concurrency construct. Para begin pair and co begin co and co begin co and means like it is in serial manner. Pair begin parent means it is executed in a parallel manner. This is fork join. Yeah. So deadlock. What are deadlock? Deadlock is like the undesirable feature of operating system. The best definition I have heard is deadlocks is the undesirable feature of operating system. The best definition I have heard. Okay, so like if there is a P1, there is a process P1 which is requesting a resource RJ, and the resource RJ is allocated to process PJ, and PJ is requesting a resource RI which is allocated to the process PI. Now, the process PI and PJ are in deadlock. PI is requesting resource PJ and PJ is assigned to PI is requesting resource RJ and RJ is assigned uh, to PJ and PJ is requesting the resource RI which is assigned to process PI. Therefore, like it became a circular wait, and PI and PJ now are in deadlock. So necessary conditions for happening deadlock. There are some condition which needs to be fulfilled if there is like a chance of happening a deadlock. First is like mutual exclusion. Second is hold and wait, no preemption of resources and circular wait. The important thing is like even if some condition like unnecessary condition like yeah, this is not will sum up what I want to say. If there exists deadlock, then all the above, all the above, which means the necessary condition are satisfied. But if all the above conditions are satisfied, then there may or may not be deadlock, which means like, okay, this is that Venn diagram which will explain. Like, if there is mutual exclusion, if there is hold and wait, no preemption of resources, circular wait, then uh, it may or may not happen deadlock. But if there is a deadlock, then these all three, like this red circle, is to be satisfied. If there is a deadlock, then all these four conditions is to be satisfied. Even if like all four conditions of satisfied, there may not be deadlock as seen by the area around the red color, which is in purple color, which means all the four are satisfied, but there is no deadlock. If resource allocation graph has only the a single instance of a resource, like if every resource has only one item, then cycle is the necessary and the sufficient condition. Cycle is the necessary and the sufficient condition to ensure deadlock. So deadlock handling strategies. One is when deadlock, like to prevent deadlock or deadlock never occurs. Second is like deadlock occurs. What we do when deadlock occurs. So first we will discuss what happen when to avoid deadlocks. First is prevention. Dissatisfying any one of the necessary condition will prevent deadlock. But how to avoid the deadlock? To avoid deadlock, if for single instance resources, we used RAG, resource allocation graph, and for multi-instance resources, we used Venker's algorithm. Okay, deadlock. If deadlock occurs, then detection and recovery is done using doctor's strategy. Doctor strategy is like it diagnose some problem and then do the cure for that. Then it again diagnose for diagnose or look for any disease. Then do the treatment for that disease if that found. So like if there are 10 process which are in a deadlock, so what will OS do? OS will first like preempt one process or preempt resource of one process and check if deadlock still persists. If it is still persist, then it again preempt like another process and goes on until the system is no longer in deadlock. And that process which get preempted during deadlock will like not save your data. Means that data is lost since the last commit or checkpoint. Or second is ignorance, which is like ostrich algorithm. Windows and Unix uses this. It is a trade-off between convenience and correctness. Like if deadlock happen, leave it as it is and keep on working with what we have. To deadlock prevention, we need to prevent or deny any of the necessary condition. So for mutual exclusion, we cannot deny this if deadlock was supposed to be happen. For hold and wait, change to we can should we will like hold and wait, we should change it to like hold or wait. Yeah, if there is a process P, then it should request all the resource prior to its commencement, and request and allocate it. Like if a process P want R1 to R10 resources, then either it get all the resources or it get none. Request all the resources prior to its commencement, but this will lead to starvation and inefficiency. Some process P1 want a resource as R10, but it is going to use that R10 in going to use the resource R10 in using the last statement of the process. Then that resource R10 is like inefficient. What it means like process P1, there is no use of resource R10 to process P1 for the initial 99% of the time, which leads to inefficiency and starvation. Like if some other process is waiting for resource R10, either if it releases all the resource before making a fresh new request, which also leads to starvation. How to deny preemption? Voluntarily release of resources. Circular wait. How to deny circular wait? A process P1, um, first of all, number all resources uniquely. Second, never allow a process to request a lower number resource than the last one requested. Like if we number all the resources from R1 to R10, and if there is a process like PI which is currently using R3, then it is only able to request resources which are numbered greater than 3, like resource R4 and so on. It will not be able to request resource R1 and R2. This way we can deny circular wait. Yeah.